Hi everyone, I'm Jae-won from Seoul National University of Korea. Today I'm going to present DIFUZZRTL, Differential Fuzz testing to find CPU bugs. This work was done by me, Suwan Song, Dong-Up Kwon, Eun-jin Baek, Jang-woo Kim, and my advisor Byung-young Lee. In 1994, the professor Thomas R. Nicely had found the Pentium FDIV bug. The bug was about the incomplete computation result of Intel Pentium CPUs. Intel has finally admitted the bug, and they have recalled all the affected CPU with the cost of $475 million, a huge amount. As you can see, since the CPU bugs cannot be fixed after the chip is released, CPU vendors such as Intel or AMD pour huge time and effort to find the possibly existing bugs before they release the chip. This process is called functional verification. Checking the CPU RTL design correctly follows the instruction set architecture. But we always find the new bugs after the chip is released. To name a few, Pentium FD bug, Ryzen RD Land bug, TSX bug, and so on. So we introduced a brand new technique to find the CPU bugs, DIFUZZRTL. We already open sourced the prototype of DIFUZZRTL, which supports the 3 real-world open source CPUs from OpenRISC and RISC-V IC. And we already found 16 new CPU bugs, where 6 of those were assigned the CV numbers, illustrating the critical impact on the security community. As the name says, DIFUZZRTL fudges the CPU RTL designs. With the advent of the AFL, the fudger has become one of the most famous tools to find the bugs in the software programs. The key idea behind the fudger is very simple. It continuously mutates the input and tests the program while increasing the coverage. So in the compile time, the fudger instruments a logic into the program, which calculates the runtime information, so-called coverage. And in the runtime, the fudger continuously mutates the input and tests the program while monitoring the coverage. So if the coverage increases, it saves the input and reuses it to further increase the coverage. This process leads to the rigorous verification of the program. To apply this powerful technique to the CPU RTL verification, we came up with 2 new requirements. First, we need a framework to test the CPUs and detect the bugs. And second, we need a new coverage definition for the RTL designs. Lots of bugs in the software program lead to the program crash, making it easier to detect. And there are lots of sanitizers such as ASAN to detect the bugs in the software. But the bugs in the CPU do not have any indication, making it hard to detect. DIFUZZRTL has to find such CPU bugs, which is an abnormal CPU behavior different from a predefined IC. For example of RISC-V, the misaligned load reserve instruction should not set the reservation. Whenever a CPU does not follow the behavior, it is definitely a bug. Like this, given an input, almost always the CPU has to be in a predefined state after executing the input. But it is difficult to automatically detect such bugs by testing the CPU RTL design alone. So we leveraged the ISA simulator, which is a software implementation of the ISA. Since the CPU RTL design and the ISA simulator follow the same instruction set architecture, they should return the same result after executing the same input. Taking this into account, we applied the differential testing on these designs. So DIFUZZRTL automatically detects the CPU bugs by comparing their result after executing the same input. But the CPU RTL design and the ISA simulator have completely different input space. The RTL design is a hardware implementation, so it needs an input stimuli injected every cycle. On the other hand, the ISA simulator requires a well-defined executable. So we define a new input format called siminput, which can be used for both the CPU RTL design and the ISA simulator. Siminput contains the entire CPU input space, including instructions, data, and the interrupts. and DIFUZZRTL runs as a test bench for the RTL design so that it passes the shim input and generates an input stimuli every cycle. Finally, we implemented the testing framework, which continuously generates the shim input and tests both CPU RTL design and the ISA simulator. While testing the CPU designs, DIFUZZRTL needs a coverage for the RTL designs, but we need a completely new coverage definition. To define such coverage, we first need to know how the RTL designs run. RTL is an abstraction of a language to describe the hardware circuit implementation. This is a simple circuit which can be implemented by the RTL languages, and the hardware designers model the behaviors of this circuit with the finite state machine, so-called FSM. So the finite state machine is constructed from the registers in the circuit, and the circuit design runs while transitioning each stage in the FSM. On the other hand, the verification engineers tries to explore as many stages in the FSM as possible, meaning that they rigorously test the design. As with this goal, we conclude that the coverage for the RTL designs should guide the input to find new states. However, all the existing coverage measures were not suitable for the RTL fudging. Branch coverage, which monitors the branch statement, is not accurate to capture the finite state. MUX control coverage, monitoring all the MUX select signals, is not efficient enough to quickly run the fuzzer. And the FSM coverage, which directly monitors the finite state, is not automatic, so it requires the manual effort from the designers. So we introduce register coverage, which is a new coverage measure for the RTL designs. Register coverage can correctly capture the FSM exploration, and it does incur only 7% runtime overhead, which is fast enough to run the fuzzer. And also, the register coverage is fully automated, so we do not require any manual effort. Since the goal of RTL verification is to explore as many states in the FSM, it is quite important to precisely capture the finite state, and we monitor the registers which construct the finite state machine. Given a circuit like this, we add one more register called leg state to monitor all the registers. Thus, the leg state represents the finite state every cycle. For example, if the 3-cycle input is given like this, for the first cycle, leg state represents RF-RS, and second, BF-PS, and so on. But it is almost impossible to monitor all the registers in the design because the CPUs have a huge number of registers. For example, with the 3 designs we fudged, the number of registers range from 200 to 5,000. So we define a new definition, control register. Control register is a register wired into the MUX select signal. Here we focus on the MUXes because they change the control flow of the circuit design, as like the branches in the software. Whenever a MUX select signal is toggled, the circuit design is activated in different way. Then we implemented a static analyzer which identifies all the control registers. So given a circuit like this, our static analyzer first identifies all the MUX select signals. Then it identifies all the control registers by performing backward tracing the wires. With help of this analyzer, we were able to reduce the number of monitored registers to at most 1 out of 10. We also want to note that our analyzer is fully automated to identify all the control registers. While monitoring the control registers, the register coverage has to identify the new state and compute the number of new state explorations. For that, we introduce a hardware data structure called coverage map. Coverage map remembers all the explored states so that we can always identify the new state exploration by checking the coverage map. Then we introduce the instrumentation method, which computes the number of new state explorations. For example, given a RTL design with 3 modules like this, we instrument all the modules with 3 components, leg state, curve map, and curve sum. As I mentioned, leg state monitors all the control registers and CUBSUM remembers all the explored states. Then we summarize the number of new state explorations into the CUBSUM register. We instrument all the control registers so that their values are hashed into the leg state every cycle. Thus, leg state represents the final state. Then, the leg state is used to index and set the corresponding bit in the curve map. For example, if the value of leg state is 4, then the fourth bit in the curve map is set 1, meaning that the corresponding state is covered. Before writing 1, we check the bit, so if the bit is 0, we increase the CUBSUM register to indicate that the new state is explored. The CUBSUM value is maintained in all the modules, so they are wired up to parent module and summed until the top level output. We used the top level output total sum of CUBSUMs as a register coverage measure. We implemented all this procedure into the compiler path so that our compiler automatically instruments the components and related logics into the CPU RTL design. Finally, we completed the fuzzer framework, which uses the register coverage to guide the input. To summarize our work, we introduced the DIFUZZRTL, which is an accurate, efficient, and automatic fuzzer to find CPU bugs. DIFUZZRTL includes the register coverage guided input generation, and it automatically tests the CPUs and detects the bugs. We implemented the prototype of DIFUZZRTL with 3 real-world open-source CPUs, MO1KX from OpenRISC, and Rocket and Boom from RISC-V. And DIFUZZRTL supports 2 RTL testing environments, software simulation and the FPGA prototyping. Once again, we found 16 new CPU bugs with DIFUZZRTL. There were a wide range of bugs, from the performance bugs to the decoding bugs. Some of the bugs we found were even harmful to the security of the system. For example, the bug found in Boom was breaking the memory consistency, which can trigger the race condition. Such bugs are much critical than the bugs in software because it could take much longer time to identify the root cause of the bugs. We also demonstrated the effectiveness of DIFUZZRTL by conducting the case study with newly found bugs, as shown in the second table. For more details, please check my paper. As a future use case, we think the idea behind register coverage can also be used to detect the microarchitectural side channel. And also, the DIFUZZRTL framework can be used to fudge the entire SoC, finding bugs such as memory consistency bug. To conclude my presentation, DIFUZZRTL is an accurate, efficient, and automatic fuzzer for the CPU RTL designs, and we found several real-world bugs with DIFUZZRTL. Thank you.